Morning, everyone. I'm going to try to be more concise today. My last video was long and way longer than necessary. I'm going to jump right into it on my little project on looking at dynamic programming algorithms in comparison to divide and conquer. So let me go ahead and share my screen on my code real quick. Just talk about it briefly. I'm changing my approach a little bit. I'm now using little abstraction so I can kind of have my tests done very similar without having to rewrite so much code. And I can include my previous testing on sorting algorithms, as well as the current one, which is on doing a binomial coefficient. Now, the main program is really simple. It allows you to enter at the command line what test you're wanting to perform. If you want to do a sort test, I do that, or you can do binomial coefficient test. And I'm doing this using a just an abstract class, base class. It just has a few methods in it, kind of boilerplate that I don't have to keep repeating. I'm going to expand on this as time progresses when I have more time to work on it, but this is what I got right now. Pretty simple stuff. It just has the, it does the timing, so it's very consistent on how my timing is done. So this is not a method that gets overridden, basically. I just use this method for all of my tests. But there are, and the validation, it runs that. This is not overridden in the subclasses. There are two abstract methods, test algorithms and validate algorithms, that are actually overridden in each subclass. For the binomial coefficient test, for the validation, I just have this kind of looks kind of funky here if you're not used to it. This is you can create tuples in C#, or in the .NET framework. Really, you can create tuples that are any number of variables stored inside of a tuple, which is a value type, not an object. It's a struct. But C#7 added the ability to create tuples without having to actually type the tuple and all the generic stuff that you can just put in parentheses your type, and you can even give it a name for each variable of the tuple in parentheses, and that will internally create a tuple struct. So I just made it a read-only class containing, so it can't be modified, containing a tuple of the value of n, the value of k, and then the result, which is C, with the expected result. And since that's a value type, it can't be changed, it's immutable, and it's stored in a read-only list, so there's no chance that I accidentally modify that in code, but it just has some known good values for binomial coefficient. And so that's how that's validated. So I can test each algorithm to make sure it is properly computing the binomial coefficient. The validation algorithm, pretty straightforward. That's just where it actually tests each one to make sure it validates each algorithm. And down here, when I override test algorithms, I'm simply calling the test, which is that internal, or not internal, but it's that method that's not overridden, that does the timing. It runs that on every single method. And in this case, I'm using three methods for three different algorithms, and I'll talk about that in just a moment. The actual test is also pretty straightforward. I went back and forth on how I wanted to do this, but ultimately I just increment n from 0 to whatever value I want, in this case 30. And as n increases, it runs a test for every value of k between 0 and n. And I do that 10 times. And that's so I can pick the smallest value, or the smallest runtime for each execution of that particular set of values. And then I only take the lowest time. And the reason for that is any kind of random noise that gets introduced is only going to slow the algorithm's execution down. And we're just going to toss that out and only use the lowest because that's the best possible performance. And that's what we're wanting to look at. So I'm only keeping the lowest score. You're never going to have better performance due to noise. It'll just be the most optimal performance. So we do that, and then we display it on the screen nice and pretty. You know, it's nothing too fancy going on there. Let's look at my actual algorithms for binomial coefficient. The first one is divide and conquer. It uses recursion to call itself over and over, of course, as we all know recursion works. And unfortunately, the drawback to that is it's performing the same calculations for results that we already have the value for. So it's very wasteful for execution time. But it is very good on memory usage because it's not creating a large array to store values. The second method right here is binomial coefficient dynamic. And that, of course, uses dynamic. I'm creating a two-dimensional array. I did not come up with these algorithms, of course. I'm not that great at math and coming up with things, but it's not too complicated to understand. But I got this off the internet, and it's creating a two-dimensional array, and it's essentially storing a Pascal's triangle within that two-dimensional array. And that way, when it's computing each subproblem, it's not having to revisit the same subproblem over and over. It's just building that Pascal's triangle. And if you do a Google for that, you'll see a nice, pretty picture of what I'm sure everybody's aware of what a Pascal's triangle is after doing this this exercise. But that's just the basic way of doing it. And that should operate at big O n times k. Keep getting messages. Anyways, then I also, to add a little wrinkle, there's an optimized version, a space optimized version of the binomial coefficient. And instead of using a two-dimensional array, it stores only the last row of the Pascal's triangle. So it only needs a single dimensional array to store that. And each time it runs through an iteration, it recalculates the next row of Pascal's triangle based off the previous row. So it's not storing at all. Theoretically, it should perform about the same speed as the other one, but it should have better memory optimization. But if we go and look at my results, let me go ahead and run this. You can kind of see what it looks like. If we run this, quickly goes through, and this is the slow one. It's doing the recursive algorithm first. And the last number you see over here in green, that is the smallest time of execution. The yellow number here is just the value of n. And now my testing, like I said, I'm testing each value of n for every value of k, 0 through n. Another way to do this would be to look at only n divided by 2, which for an even number, n divided by even value of n divided by 2 for your k will always have the most operations required. So that would be another way to test it. It might give you a better idea on your chart of the actual performance. So mine's doing, of course, extra steps, so it's not going to have the same curve on the chart. In fact, it might look a little more linear. It'll look more linear with only calculating that single value for each. But as you can see, the execution time of dynamic and dynamic space optimized were much faster. They completed nearly instantly. On this particular run, it took 3,142 milliseconds to just do a value of 30 for n, whereas the other ones less than a millisecond. you know, it's very, very fast execution time. So let me go ahead and switch over to my spreadsheet so I can actually see some, y'all can see some charts. Let's see here. Look at these charts. All right, if we look at this is the data from one of my runs for just 30 for the max value of n. And you can quickly see that divide and conquer grows very fast in its time complexity. In fact, when you look at its chart, you can't even see the dynamic algorithms registering unless I change this to a, you know, I could probably change this to a logarithmic scale, and then you will see, of course. And one interesting thing to note is at very low values, divide and conquer doesn't perform bad. In fact, it's slightly better than the first dynamic programming algorithm. But of course, it starts growing very fast in time of execution. So then, since that you can't really see much on that, and it's clear that it's performing way worse, let's look closer at just the two dynamic algorithms. Now, this is where the results really surprised me. I didn't expect to see this much difference. I expected maybe a slight performance increase on the space optimized, but there was a pretty good performance difference. So I wanted to look at that a little closer. So now I'm going to run 200 operations, and keep in mind each one of these iterations is performing 10 operations, not 10 operations, 10 executions of that method, and then I'm taking the lowest score once again. But when we look at 200, now we're seeing even more that there's a big difference in performance between these two. And now, like I said, keep in mind, I'm running it for every value of k between 0 and n. So it's not going to be as linear as it would be, because it's doing a lot more executions of the method. But still, that dynamic one without space optimization is growing in time quite a bit greater. I have a theory on that, a couple theories. One is that based on my research in the .NET framework, it optimizes array operations for single dimensional arrays. So looking up an index on an array is always optimized for single dimensional arrays. Two-dimensional arrays are going to perform worse. Now, not just C#, but the .NET framework allows you to have jagged arrays, which is essentially an array of arrays. And from my understanding, arrays of arrays are better performing. So it would also be possible to create a jagged array where each row is only the necessary width required for that row, or the number of columns. So you could also have better space optimization just by using jagged arrays if you coded it properly. But the other possibility is obviously that there's something else going on in that algorithm. I don't really see how it's changing it that much, other than just the array, the way it's storing the arrays and calculating each new row based on the previous row. But that's what I got. It's but there's definitely a good difference going on there. Looking at my report, I kind of explore that a little bit in depth, but it's not. I'm not 100% sure what's going on there. In the future, I would like to test that. Just simply modify that algorithm to use a jagged array rather than a two-dimensional array, which a jagged array in code would look like that, basically. Of course, you'd have to change. I would have to look at how I hardly ever use jagged arrays. I have to relearn that real quick, but that's essentially what a jagged array looks like. So it's an array of arrays, but I would like to try that out just to see how it performs. It'll be interesting. Another thing I'd like to do is change my test and just only test basically where k equals n divided by 2, instead of I'm doing, as you can see right here, every value of k from 0 through n. So that might be something to test. I know some of that stuff looks weird. I'm calling func right here, and what that's doing is it's passing in, this is passing in the actual method. So func right here is calling, when it runs it the first time through, it's going to run it using that method. The next time it calls func, it's going to be doing it with this method, and so on. So it can test each one. It just makes it easier to add in other algorithms without having to write a whole bunch of extra code. But yeah, one thing I've changed is I'm now going to store all my exercises in one Git repo. I'm going to try to do that, and if I can continue using a single test application, test console as I call it, then I can just keep adding algorithms and things up here. I have my sort algorithms in here and the binomial coefficient algorithms, and that's just referenced by this particular project. It just references the algorithms assembly or project. That way I can kind of keep it all nice and organized. And I just want to make it so I'm not having to write so much boilerplate code over and over. Just want to have, I can just kind of plug in new stuff and play around with it. So some other things I want to add, and there's some nice open source projects out there that I could easily implement in here that would allow more powerful control of the arguments that are passed into main. So I could do things like, and I could do it manually myself, but it's just, those frameworks are really nice. They give you a lot more options. But I could pass in, so if I'm doing a sort test, I could also pass in the number, the size, the max size of the arrays, how much I want to iterate each iteration by, or how much I want to increase each iteration by. I could add in, when you type in binomial coefficient, you could also give it the value for the max value of n, and how many times you want to test each value of n, and then take the smallest value of that. I could add in other options essentially, and then you can just type them in the command line, and you can easily change your test procedures. Right now, if I want to change my test procedures, I just go in and manually change things, which is fine, but you don't want to keep making those changes into Git, because it doesn't really make much sense to do that. But anyways, I hope this was interesting. I hope it was not near as painful to watch. I highly doubt anybody watched my entire hour-long video, but hopefully you might have watched a little bit and got something out of it. But I'm having fun in the class. I've said before, if anybody wants to group up or work together on this, that'd be great. I'm really busy. Like I said, I'm working a lot of hours and whatnot, but I'm having fun, and that's the main thing, right? We all enjoy doing this. So I hope everyone has a great day, and thank you for your time.